Okay. So, next come to that your solution of that problem, right. So, P loss is equal to, this is given 0.001 into Pg2 minus 70 square, say whole square. So, take the derivative with respect to your what you call that Pg2, right. So, dP loss by dPg2 is equal to 0.002 Pg2 minus 0.14, right. You take the derivative. Now, that L1 is given, right, L1 is given, that is 1, that is known, not given, actually L1 is 1, it is known always, right. Now, L2 is equal to 1 by 1 minus dPL upon dPg2, because we have assumed that Li is equal to 1 minus your dPL upon dPgi. dPL means P loss, this there should not be any confusion that it is loss actually, right, because loss is a function of Pg2, Pg3, Pgm, here of course it is only Pg2. So, this one, so it is 1, then dP loss upon this expression, this dP loss by dPg2 this expression, right, this expression you substitute here, you will get 1 upon after then 1 upon 1.14 minus 0.002 Pg2, right. Now, L1 into dC1 dPg1 is equal to 0.35 Pg1 plus 41 is equal to lambda. This we know, you have seen just now, right. So, anyway L1 is equal to 1 and L2 into dC2 by dPg2 is equal to 0.35 Pg2 plus 41. This is actually same ICs divided by your this thing what you call into this L2 into L2, that is 1 upon this one. So, it is 1.14 minus 0.002 Pg2 is equal to lambda. This is equation 1, this is equation 2, right. And from equation 1, right, from equation 1 you can get, from equation 1 you can get Pg1 is equal to, right, Pg1 is equal to, you will get lambda minus 41 by 0.35, and from equation 2 you will get Pg2 is equal to 1.14 lambda minus 41 by 0.35 plus 0.002 lambda. So, Pg1 lambda, this equation is linear, L1 was 1, right, but Pg2 is equal to lambda, numerator lambda is there, this is also numerator also lambda, this is non-linear. So, direct solution you will not get, you have to get solution iteratively, right. So, I have made some thing for which lambda is equal to 117.6 rupees per megawatt hour. This is more or less optimal value. Later when you will go for gradient method other thing, this particular example you will solve of your own iteratively, right, later when I will explain everything, right. So, Pg1 you will get 218.857 megawatt and Pg2 will get 115.029 megawatt, right. So, that is iteratively has been solved. You have to start with some initial value of lambda, then you solve it, right. So, next is that power loss, that expression was given, that P loss is equal to 0.001 Pg2 minus 70 whole square, Pg2 is 159.029 minus 70, you substitute here Pg2 value, it is 7.926 megawatt. Now, as a check, Pg1 plus Pg2 minus P loss, right, how much it is coming? It has to become load. So, it is 218.857 we got plus 159.029 minus 7.926 megawatt. So, this is coming 369.96 megawatt, approximately is equal to PL1 plus PL2. PL1 is 300 megawatt, data it was given, PL2 70 megawatt given. So, total 370 megawatt. So, that lambda is equal to your 117.6 is the correct solution. Now, physical significance of lambda considering losses, right. So, you will see the same physical significance whatever we have seen without losses, right. So, from equation 16 we have seen that delta Ct is equal to I is equal to 1 to m dci Pgi0 dPgi into delta Pgi. So, rewriting this equation, now numbering again 35, right. Next is the power balance equation is written as sigma I is equal to 1 to m Pgi total generation, because of small change of load this has happened, change in generation, change in loss, minus delta P loss is equal to delta PL. This is equation 36. Now, what we have to do is we have to go for that again that 2 term Taylor series expansion. Now, due to increments of load from PL0 to PL0 plus delta PL, correspondingly optimal PI0 also has changed, right, from PGI 0 to PGI 0 plus delta PGI. Therefore, line loss expression also, because it is a function of PG2, PG3 up to PGM, right. So, P loss is equal to P loss PG2 0 plus delta PG2, PG3 0 plus delta PG3 up to PGM 0 plus delta PGM, that is equation 37, right. So, because of load change, generation and loss also will change, right. Now, this expression, that expanding the above expression by Taylor series and retaining only the first two terms. So, this one can be written as P loss is equal to P loss 0 plus I is equal to 2 to m del P loss del PGI, your PG 0 is function of it is your all the PG2 0, PG3 0, that is why you are making PG 0 in general into delta PGI, right. Therefore, delta P loss is equal to I is equal to 2 to m del PL loss PG 0 del PGI into delta, this is equation 39. So, equation 36 and 39 from this thing we get, right, this one, that here add delta PG1, subtract delta this thing, equation 30 and 39, yes. What you can do is that this is your delta P loss is your P loss delta P loss is this one, right. Now, what is your equation 36 and 39, equation 36 is here, right. So, your then delta P loss you substitute here, delta P loss you substitute here, right. So, from that you will get that with this equation it is writing 1 to m, you can write this equation as, I mean you can write like this, you can write like this, your delta your this thing, that hold on, then this equation I is equal to 1 to m delta PGI minus delta P loss is equal to your delta PL, right. That means, this your what you call this equation you can write delta PG1 plus sigma I is equal to 2 to m, this PG1 is taken out. So, delta PGI minus delta P loss is equal to delta PL, that is the total load, right. Therefore, this your what you call and your delta P loss, this delta P loss is equal to your this thing, here it is delta P loss is equal to I is equal to 2 to m del P loss delta PGI into PGI, right. Therefore, this equation you can write that equation 36 and 39, right. Then equation 36 is here, equation 36 is here, right. So, this equation you can write your this thing, this equation you can write that delta PG1 plus I is equal to 1 to m 1 minus delta P loss delta PGI this thing, right. Delta P your delta P loss delta PGI, then you take delta PGI common, because delta P loss is equal to this one, right. That means, this equation actually you break it delta PG1 plus I is equal to 2 to m delta PGI minus delta P loss is equal to delta PL, right. The delta P loss expression you substitute, delta P loss expression you substitute, and then you can get this equation delta PG1 plus I is equal to 2 to m 1 minus del P loss del PGI, again and again not telling that function of PG2, PG3 and so into delta PGI, this is delta PL. So, I need not do this small thing, right. So, this one I have shown you, this one I have shown you, right. This here you put the delta P loss expression, right. So, that means your this is your this equation is marked as 40, this is equation 40, right. So, this one actually that this one actually you know that Li is equal to 1 minus 1 upon 1 minus del P loss upon del PGI. So, it is 1 minus means it will be Li inverse, that is 1 upon Li, this is actually 1 upon Li. That means this equation your I is equal L1 is 1, we know that, right. So, the terms in the bracket are reciprocal of the penalty factors Li, because we have taken Li is equal to 1 upon 1 minus this one. So, it is reciprocal 1 minus delta P loss upon delta P is a reciprocal of Li, right, and we also know that L1 is equal to 1. Therefore, equation 40 may be written as, because here it is L1 is equal to 1, that means here it is something like this. I am writing just one word, I am writing 1 or 2 line for you, such that you will understand, right. So, this equation, that equation 40, whatever you have got, this equation 40, this also can be written as, if for example L1 is equal to 1, then this equation also can be written as your L1 then delta Pg1, because L1 is 1 anyway, we are putting like this, plus I is equal to 2 to m in bracket 1 minus delta P loss, it is function of Pg, understandable, it is function of Pg, understandable, delta P loss divided by this one, right, bracket close, delta Pgi is equal to delta PL, right. That means, this equation, it can be written as like this, that your sigma I is equal to say 1 to m, right. So, then in bracket you can write this one also, you can add this is actually L1, that will be L1 inverse also 1, that is reciprocal of L1 is 1, right. So, this is actually this equation 1 minus this one, first make it like this, right. This is you write L1 inverse, although L1 is 1, reciprocal of 1 and this inverse, right. That means, L1 inverse delta Pg1 plus this one you can write I is equal to 2 to m Li inverse delta Pgi is equal to delta PL. In general, you can write this one, that I is equal to 1 to m, right, Li inverse delta Pgi is equal to delta PL, right. L1 is 1, that means L1 is 1. So, 1 by L1 is also 1, right. So, they are writing L1 inverse, and this is your Li inverse. So, that means in general that this equation if you make it together, then it will become your this thing Li inverse delta Pgi, but note that L1 is equal to 1, right. So, since we know that Li into ICI is equal to lambda, because this we have seen earlier, right, then from equation 35 and 41 you will get this one, right. So, this we know Li ICI is equal to lambda, Li ICI is equal to actually lambda, then from 35 and 41 just you will get it, that delta CD will be actually is equal to delta CT will be lambda I is equal to 1 to m Li inverse delta P is equal to lambda into delta PL. This is very simple actually, go 35 and 36 and just put it, you will get it there, right. That means, what does it mean? Ultimately, the whole thing actually is becoming delta CD is equal to CT is equal to lambda into delta PL, same as before. That means, the above result is the same as equation 18, right, and that is lambda represent the increment in cost rupees per hour to the increment in the load demand, this thing same, whatever we did without loss or with loss, the meaning is same physical significance, right. So, next one is, so up to this, that we have seen the penalty factor, that lambda Li, that is in terms of this thing, your what you call that derivative of the power loss with respect to generation, except your generator 1, right, and L1 is always 1, and your otherwise same philosophy Li ICI must be is equal to lambda, that is equal lambda basis, right, and physical significance of change in load also same as without considering the losses, right. Only thing is that the derivation actually whatever little bit mathematics is, that very simple, just little bit practice you do and you will find things are very simple, and problems are also not that difficult as far as classroom exercise is concerned, right. Next we have to go for some procedure, right, that how to determine the lambda, we will go for this using gradient method, right. So, for example, in example 4 we have seen that an iterative process is necessary for determining the value of lambda. Previous example we have taken and we saw that Pg2 is a function of lambda, but relationship is non-linear, right. That means we have to follow some iterative process for finding out the lambda, right. So, what you do, a rapid solution can be obtained by the use of the gradient method, right, gradient method when losses are considered, right. So, what we will will solve both the cases. First we will consider that without any loss, and that we will consider the losses, right. So, equation from equation 13 we know that dci upon dpgi is equal to lambda, right. So, this we have seen from equation 13, right. So, that means that Ci actually is equal to ai plus bi pgi plus dpgi square. So, when you take this bi plus 2 di pgi is equal to lambda, right. That means pgi is equal to lambda minus bi upon 2 di. This is equation 43. Now, we are trying to find out lambda using gradient method, right. So, what one can do is just look, things are very interesting and very simple, right. And so, actually when loss is not considered, just hold on, when loss is not considered, the total generation is equal to total load. This is from equation 10, right, that is the thing. That means, from equation 44 and 43, right, that you can write that is Pgi is equal to lambda minus Bi upon 2 di. So, what you can do is, right, that you take your this thing both side, your what you call that sigma Pgi is equal to your PL, right. That means, if you take this equation, I am rewriting for you, if it is Pgi is equal to lambda minus Bi upon 2 di, this is the equation. You take sigma on both sides, right, summation, that I is equal to 1 to m Pgi is equal to sigma I is equal to 1 to m lambda minus Bi divided by 2 di, right. If you take your summation both the side, right, and total generation, that is equal to total load, because this is the total generation, that is equal to total load. That means, total load is equal to actually I is equal to 1 to m lambda minus Bi upon 2 di, di is the suffix, right, I is the suffix. That means, this equation, that is why writing from equation 44 and 43 that I is equal to 1 to m lambda minus Bi upon di is equal to total load, right. That means, this equation you take summations both side, and that is equal to summation of generation load. That is why this equation we are writing here, this is equal to PL, that is equation 45, right. From this equation you write lambda is equal to this expression, because this equation I am writing for you, right. So, this equation, that sigma I, this equation only you can this equation only we can write like this, that I equal to 1 to m, right, this is your lambda by 2 di minus Bi by 2 di is equal to PL, right. This is the thing. Therefore, this equation, this your what you call this one, you can write lambda I is equal to 1 to m, right, 1 upon 2 di is equal to PL plus sigma I is equal to 1 to m Bi upon 2 di. So, lambda is equal to divided by sigma I is equal to 1 to m to this thing 2 di. That is why this equation is writing lambda is equal to PL plus I is equal to 1 to m Bi upon 2 di divided by I is equal to 1 to m 1 upon 2 di. This is equation 46, right. Now, this one. Now, this part you have to understand. Now, this is actually lambda is a PL, lambda is equal to this is your PL plus all these constant. I mean, lambda is a function of PL, right. Now, this that means this equation, let us define equation 45. You define this equation 45, right, this one you define this equation as your function, because this PL is a function of lambda, right, and lambda is a function of PL. So, PL is a function of lambda, you define f lambda is equal to PL, but not only that, this one also you have to see that your PL is equal to, this is your PL, right, PL is equal to I is equal to 1 to m lambda minus Bi divided by 2 di, right, this is the thing, and this is actually nothing but your total total I is equal to 1 to m, PL is equal to total generation. That means, if we take that it is PL is a function of lambda, that means we are writing f lambda is equal to PL, that means we also can write, because delta summation of generation also is a function of lambda, right. That means, we can also write f lambda is equal to your what you call your this thing that sigma I 1 to n, that is also function of your this thing generation, right, because generation is also function of lambda, PL is also function of lambda. So, we can write f lambda is equal to PL, also we can write f lambda is equal to I is equal to 1 to m, it is PGI, this one also we can write, right. So, this is actually let me write in clearly, f lambda I equal to 1 to m PGI, right, because this is also function of lambda, this is also load is equal to generation, loss is neglected here, right. That means, this is now what we can do is expanding the left hand side of the above equation, I mean this equation in Taylor series about its operating point lambda k. Say at some iteration k, right, you expand it in the Taylor series and only consider the first two terms, right, some operating point, right, and neglect the higher order term. Then what we will do, you will get f lambda, k means kth iteration, say k some value, plus derivative of it df lambda d lambda at kth iteration. So, again and again I am not uttering k, right, understandable, into only this time delta lambda is equal to PL. This is that your what you call the Taylor series expansion for the first two terms for any operating point. That means, from this equation delta lambda at kth iteration, that PL minus f lambda k upon df lambda by k, df lambda d lambda at kth iteration. This is equation your 48. That means, this is my f lambda, right. Now, once again your this thing. Now, that means delta PGK, right, just hold on, that means delta PGK, this delta PGK can be written as the total load minus f lambda k, right, because PL load is fixed. Idea is this one, I have just told you that idea is where I have kept that one, idea is that f lambda, just hold on here, that through the iterative process that load is not changing, PL remains same, right, but f lambda that f lambda also can be written as function of generation I is equal to 1 to m. So, PGI is changing in every iteration, but load is fixed, but f lambda PGI is changing in every iteration, because this is also lambda is changing in every iteration, right. So, that means, this one you can make it that your what you call that delta PGK is equal to, you can write PL minus f lambda k, because every iteration you have to find out this f lambda value, right. That means, delta PGK is equal to PL minus I is equal to 1 to m PGI k, because f lambda this f lambda I told you, this f lambda I told you this one, that f lambda is equal to, I told you that I is equal to 1 to m PGI. Therefore, at kth iteration, if you put kth iteration, then this is also k, right. That is why that this one can be written as f lambda k is equal to this one also, right. So, that means, your what you call that PL, that is that f lambda is equal to write PL as well as f lambda you write this one. If you do so, then then this can be written as, that is a mismatch, right, between load and sum of generation actually. So, delta Pgk will be PL minus I is equal to 1 time Pgk. So, this is actually equation 50, right. Now, also we know f lambda is equal to I is equal to 1 to m lambda minus bi upon 2 di. You have to obtain, because you need the derivative of this one also with respect to lambda, because here you need this derivative in equation 48, right. That means df lambda d lambda is equal to I is equal to 1 to m 1 upon 2 di sigma I is equal to 1 to, if you take the derivative with that, it will be sigma 1 upon 2 di. This is equation 51. That means, in this expression this df lambda d lambda at kth iteration, you substitute, this is a constant actually, for this case it is a constant because 1 upon 2 di only, right. And this expression and this expression you have to call this delta Pgk expression, delta lambda k, it can be written as delta Pgk, because PL minus f lambda k in equation 48, PL minus f lambda k is equal to actually delta Pgk, right. So, in this equation we are putting in 48 delta Pgk, that is why it is written here that from equation 48, 49 and 51, delta lambda k will be delta Pgk divided by I is equal to 1 to m 1 upon 2 di, this is 52. So, at any iteration k plus 1th iteration, lambda k plus 1 will be lambda k plus delta lambda k, right. So, this is equation 53. The process will be continued unless and until delta Pgk is less than a specified accuracy, k is the iteration count, right. So, this f lambda is equal to PL and f lambda is also is equal to sigma of all the your generation Pgi, right, because both are function of lambda. So, there should not be any confusion for you, right. And this is your what you call numericals, so we will take later, right, but this is your this concept should be clear, right. So, this is for without your what you call losses. Now, if we consider the loss, right, so determinants of lambda considering losses. So, what happened actually, that this loss formula, before saying anything, whatever you see it here, I is equal to 1 to m, j is equal to 1 to m, Pgi, Bij, Pgj, right, this will be derived at the end. Right now, I do not want, then this whole continuity will be lost actually, and you will be also thinking that after that suddenly this is coming. So, this formula for the timing will assume that this is your what you call, this is given, but I will derive it for you. It will take some time, but I will derive at the end of after making all these things, that loss formula, right, and how and all the B coefficient also how one will get it. Now, one common practice actually is to express the total transmission loss as a quadratic function of the general power outputs. The simplest quadratic form of loss is P loss is equal to I is equal to double sigma, I is equal to 1 to m, then sigma another j is equal to 1 to m, Pgi, Bij, Pgj. This is equation actually 54, right. From equation 30 actually we get dci upon dpgi plus lambda dp loss dpgi is equal to lambda, that is I is equal to 1 to m, right. This is equal, this is actually your equation your 55. You go back to equation 30, this equation actually written there, right. It was written actually that your lambda, if you take your what you call, it is lambda into your, this way it is written, no, that your basically we know, no, this one it is written, no, dci I am writing, I am not going to equation 30, I am just writing here, this one is equal to lambda minus lambda dp loss, then dpgi, that is lambda common 1 minus dp loss, then dpgi, right. That means lambda is equal to dci dpgi divided by your 1 minus dp loss, then dpgi, this one we have made, no, and this is your we have made li, right. So, from that equation 30 only we are getting this formula dci dpgi plus lambda is equal to this one. This is equation your 55, right. So, and this equation, if you take the derivative of this equation with respect to PGI, it will be your what you call 2 into your j is equal to 1 to n Bij Pgj. This is equation 56. Thank you. I am coming again. Thank you.